Welcome, everyone. This is the first Combinatorics seminar of the new year. Hopefully, everyone's enjoying the new quarter. We're very happy to have Shira Zerbib from Iowa State University, and she's going to talk to us about how to divide multiple cakes fairly using topology. And feel free to ask any question during the pre-seminar. Take care.
Thank you so much. Thank you for the invitation. I'm very happy to speak at your seminar, and I wish I could visit in person, but maybe next time. So I will start by giving a very informal introduction to some of the concepts that I'm going to discuss in my presentation later. So I'll do that using the board, and you're welcome to stop me at any time and to ask as many questions as you want. And please feel free to ask anything you don't understand or you want to know. So I will start with very, very basic concepts and work along some more involved notions later on. So we first start with the simplex. So when I say simplex, I will denote it by delta n-1. This is the n-1 dimensional simplex. I will always think of it as embedded in the standard way in Rn. So this is the convex hull of the basis, standard basis vectors E1 to En in Rn. So delta 1 will be this segment where this is 0, 1, and this is 1, 0 in R2, and delta 2 will be this triangle in R3. This is 0, 0, 1, this is 1, 0, 0, 0, 1, 0. All right. So we can write this as the set of all n tuples, x1, xn, where the xi's are non-negative and their sum is 1. This is just writing this convex hull explicitly. And we can observe then that each such point in the simplex corresponds to a partition of the 0, 1 segment. So into n pieces. So how do we do that? We take the first piece from the left to be of length x1, and then the second piece to be of length x2, and so on. And the last piece will be of length xn. And since the sum of all the xi's is 1, this is exactly a partition of the segment 0, 1. Okay, so let us just make some observations about how these partitions look, given where, in what phases these points lie in the simplex. Okay, so let us take the two-dimensional simplex, E1, E2, E3. And let us take some point here, x1, x2, x3. Okay, so as we said, this corresponds to a partition to three pieces. This is of size x1, this is of size x2, this is of size x3. Now, what would have happened if I, instead of some point in the interior of the simplex, I took a point in the boundary of the simplex? So for example, let's take the point E1, which is 1, 0, 0. So this corresponds to 1, 0, 0. Do you still see my board well enough? Good. So this corresponds to the partition where the first piece is the entire cake. So this is 1, x1 equals 1. And the two other pieces are of length 0. So we have 0 here and another 0 here, right? So the two other pieces, I will call them throughout my presentation today empty. They're not really empty because they have they have a boundary of 1 point, but their interior is empty, so I will abuse notation and call them empty. Okay, similarly, if we take a point, say, on this face, so it will have x1, x2, and 0 here, then we will get two non-empty pieces, x1 and x2, and an empty piece here the third piece will be empty. Okay, so we observe that if a point lies in a face that is the convex hull of some set of vertices EI1, EI2, EIK, then the only non-empty pieces are the one corresponding to the vertices that lie in this face. Okay, so if a point is in the face 1, 2, then the only non-empty pieces can be either the first piece or the second piece, but not the third piece. Okay, questions about this? Good. Okay, so now I will discuss a few very well-known lemmas about the simplex. So the first one that I think is quite well known, so probably a lot of you heard about it, is Sperno's lemma. And this is from 1989. So Sperno tells us the following. So suppose we have the n-dimensional simplex, and suppose we have a triangulation of the simplex. Any triangulation you can think of. And suppose we have n colors, and we color the vertices of the triangulation with these colors, but in a very special way. So the vertices of the simplex are colored by 3 different colors. And now, if a vertex lies in a face that its vertices are colored by some colors, then it must be colored by either one of the colors of its vertices. So a vertex here must be either red or green. So say I color these 2 red and this one green. And a vertex here must be either green or blue. Then say this one is green. And a vertex here must be either blue or red. So say blue. And inside I can color them however I want. So say blue here, and I don't know, let's take green here. Okay, so Sperno tells us that if we color the vertices of any triangulation of the n-dimensional simplex in such a way, then we can find a simplex in the triangulation that is colored by all the colors. So here is one. such simplex. It is colored by all three colors. Okay, so now I want to mention a somewhat less known version of Sperno's lemma that is called the KKM theorem. KKM theorem, and this KKM stands for Knaster, Kuratowski, and Mazurkiewicz, and this is from 1928. And it is a continuous version of the Sperno's lemma. So now, again, we have the simplex, but instead of having a triangulation and coloring, we have sets covering the simplex. So we have sets, say A1 to AN, where n minus 1 is the dimension of the simplex. And these are closed sets. And they cover the simplex, but in a nice way. So what do I mean by nice? So vertex E1 must be in A1. Vertex E2 must be in A2. And the face 1, 2 must be in the union of A1 and A2. So we have something like that. And similarly, vertex E3 must be in A3, and the face 1, 3 must be in the union of A1 and A3, and the face 2, 3 must be in the union of A2 and A3. So we have something like that. Okay? Other than that, we have no other conditions on the AIs. They don't have to be convex, they don't have to be connected, they don't have to be anything but closed and satisfy this nice condition. And the theorem tells us that if I have such a KKM cover, then the intersection of all the three sets must be non-empty. I have some non-empty intersection here. So let us write this condition mathematically. Every face sigma, we have that sigma lies in the union of the AIs, where I is a vertex, where EI is a vertex of sigma. Okay. And the conclusion is, so if this is true, then the intersection of all the AIs is non-empty, where I goes from 1 to n. And you can see why this is, in fact, very easily proved one from another. So here we have only a finitely many points that are colored. Here you can think of it as all the points of the simplex are colored, and the sets are the colors. The sets represent the color for which every point is colored. Okay, any questions about that? Later on, I will discuss a colorful version of this theorem, where instead of having one KKM cover, we have n KKM covers of the simplex. And the conclusion of the theorem is that we can choose one set from each of these covers and still have a non-empty intersection. But I will discuss it later on.
Sorry, I wanted to ask.
Yes,
in this KKM theorem, do you need that the AIs cover the simplex?
Yes, this is a cover of the simplex. And you can see it also from this condition, because if you take sigma to be the entire simplex, then it should be in the union of all the AIs. Okay.
Cool. Yeah, I didn't realize that sigma could be the entire simplex.
Yeah. This is true for any face, including the simplex itself. Any other questions? Okay, so now I want to switch gear and to discuss some matching theory in hypergraphs. So let me tell you in advance while I erase my board that all the things that I will discuss about cakes is actually just motivation for discussing a certain type or a certain family of hypergraphs and investigating the matching number of these special kind of hypergraphs. So I want to tell you some about matching theory. So a matching in a hypergraph H on vertex set V and edge set E is a set of pairwise disjoint edges. Okay, so we have edges in the hypergraph, and each two of them cannot intersect. If we have such a set, this is a matching. We denote by mu of H. This is the matching number of H. Is the largest size of a matching in H. So for example, if our hypergraph H is the graph, the complete graph on 3 vertices, a triangle, then what is the matching number of H? So every 2 edges here intersect. So we cannot find 2 edges that are disjoint. So the matching number is 1, right? The largest size of a set of disjoint edges is of size 1, right? Okay. Now we want to define a fractional matching. So a fractional matching, so first we can think of a matching as a function that gives every edge either 0 or 1, where we cannot have 2 edges that intersect in a vertex, both getting 1, right? Because then we have in our matching 2 non-disjoint edges, right? So it's a choice function that has the property that on each vertex only 1 edge gets 1. Okay, so we can generalize this fractionally and say that the fractional matching is a function f from the edge set to of the hypergraph now to any number between 0 to the segment 0, 1. So an edge can get any number between 0 and 1 and not just 0 or 1. This is the reason it is called fractional, because it can get fractional weights. But such that on every vertex, I don't see weight more than 1 on its adjacent edges. So for every vertex in V, the sum on all the edges that contain V of the weights of these edges is not more than 1. Okay? So if we go back to our triangle example, I can give 1/2 to each one of these edges. And this will be a fractional matching because on every vertex, I see that the weight of the edges containing it, the sum of them is not more than 1. Actually, it is exactly 1 in this example. Okay. And the fractional matching number will be denoted by nu star of H is the sum of all the weights. So the size of the fractional matching is the size of all the weights. And the fractional matching number is the maximum over all fractional matching of the size of the fractional matching. So here, in this case, F is 3/2, and this is the best possible. So we can show that nu star of H is 3/2. So going from matching to fractional matching, we can actually improve the size that we get. So here, the best we can do is 1, and here we get 3/2. And this is true in general. So nu of H is always less than or equal nu star of H. This is just by definition, because here we are taking a maximum over a larger set. And what Kennig's theorem tells us, this is from 1931, is that if G is bipartite, a bipartite graph, then nu of G equals nu star of G. So as you see, this is not true in this graph, and indeed, a triangle is not a bipartite graph. Okay. Do I still have time to introduce something, or?
Yeah, I think so. You have about 6 minutes left.
Oh, I have a quick question.
Yes.
Is it possible to use some linear programming to solve the fractional?
Yeah. Yes. So the dual notion to fractional matching is a fractional cover. I will not discuss this in this talk, but yes, if we want to discuss fractional covers, then we can see using linear programming duality that in any hypergraph, the fractional matching number equals the fractional covering number. And this is by definition always less than or equal the covering number. And this is by definition always more than the matching number. So yes, this is linear programming duality. Okay. So I want to mention a few other notions. So I
think
yes.
there's another question in the chat.
Yes, what is the question?
When discussing hypergraphs, can edge also mean an edge with more than 2 vertices?
Yes. So edge in this talk will be an edge in a hypergraph. And if I don't say any other condition of on the hypergraph, it doesn't have to be uniform. So edges can be of different sizes. And an edge is a set in the hypergraph which can contain any number of vertices. In the examples that I gave here, I discussed mainly graphs because it is more maybe easy to grasp. But in general, these notions work with any hypergraphs. A special type of R-uniform hypergraph in which all the edges are of size of a given size R is an R-partite hypergraph. And H is R-partite if, so H always has vertex at V and edge at E. And it is R-partite if we can partition the vertex set into R disjoint sets such that every edge intersects every VI exactly once. So E intersection with VI, the size of this intersection is exactly 1 for every I. Okay, so the hypergraph will look like that. We have R sets of vertices that we call vertex sides of the hypergraph. So this is V1, this is V2, this is V3, this is V4, and every edge takes exactly one vertex of each side. Okay. And the special type of hypergraph that I want, that are maybe the real subject of this presentation, is a subset of the family of R-partite hypergraph, and this will be called fractionally balanced hypergraphs. So fractionally balanced hypergraphs are first R-partite hypergraphs for some R, but with special additional property that I will explain in my presentation because I don't have time to explain now. But the first thing we have to remember that fractionally balanced hypergraphs are R-partite hypergraph for some given R. Okay. All right, so I think it's a good time to open my.
Okay, let's unmute ourselves and clap for this really nice first seminar.
Thank you.